Welcome back, everyone, for the afternoon session, or rather the only afternoon session. Thank you to all the organizers for organizing this really wonderful workshop / symposium. Thank you to Allan, who's not here. We are hoping he'll show up within minutes. Philip especially is hoping that he'll show up soon. I'm sure he will. And it's interesting that there are people from all phases here of Allan's past, and some of us, I don't know if anyone is here from his NRC phase in Canada. I don't think so. And then there is a large subset of us here from his Bloomington, Indiana phase of his working career. I'm one of them. There are many others, some of whom I have not seen in years. Some I see off and on. And then, of course, there's a large number of folks from his UT Austin days and the larger world of collaborators. Anyway, it's all nice to see you all here. We'll get started with the session. The first speaker is Philip Kim, who will talk about anions and quantum materials. Philip, you have roughly half an hour.
Yep, thank you. Thank you very much. Okay. It is my great pleasure and honor to be here, invited, and giving a talk on behalf of Allan, who is missing here. But nevertheless, we can celebrate Allan's achievement. So maybe I can start from the kind of stories about the Allan. So I think Allan is coming here, so I will wait kind of 30 more seconds. Yeah. Sorry, Allan, I was starting without you. So I think probably my role here is a little bit of the bridging between the kind of historical times of the Allan kind of going through, and this morning we heard some part of stories about the magnetisms and kind of 2D material, 2D electron system, gallium arsenide. I suppose I engineered this talk that I'm going to give a talk after Jim Eisenstein. So I was trying to refer a lot of the Jim, but Immanuel took really nicely, including gallium arsenide, and then kind of brings time into around the beginning of the 2004, where the very first 2D material graphene comes around. In 2004, the graphene was discovered experimentally by Andrei Geim and Kostya Novoselov. And soon after that discovery, there's some intriguing phenomena such as quantum Hall effect is even observed in there, and start kind of bring this interest and the excitement from also generally 2D material system, 2D electronic system, which actually grown out from the gallium arsenide heterostructures, right? And there, of course, the Allan, as just coming from the quantum Hall communities, from the very beginning of the graphene research, plays a very important role and kind of teaches a lot, especially the person like me who comes from the nanotube community, don't know anything about the quantum Hall system. From the beginning that I learned a great deal by just talking to Allan, and Allan just guided me through basically into the system, through this in the past 20 years of the research. From the beginning, it is clear the graphene has a rather unique properties, not only Dirac dispersion relations and then some topologies related with the Valley-Chern numbers is one thing, but also it has kind of interesting degree of freedom, which is kind of two valley, also kind of two spins, typically. And altogether, this forms so-called the SU4, the pseudo spins, the space, which turns out kind of plays a very important role. And it was kind of Allan's kind of very seminal paper with Kentaro Nomura, published in 2006, or that's already kind of guide us that indeed this the how to orders or how to manipulate this SU4 spin is kind of very important. And kind of shortly after follow through the again paper by the Konyang, the Summer, and the Allan MacDonald, they're all here, kind of quickly pointed out that indeed the SU4 symmetry is kind of really important ingredient to understanding this the graphic system graphene. And as well as also this one that kind of carries out on not only graphene, but many of this triangular two-dimensional system where usually you have additional value degree of freedom plays a role. So you will see that throughout this kind of next 2 days, that whenever it comes with the 2D materials, and indeed how we understand this kind of multi-component of this degree of freedom becomes quite important. And that's kind of something that very important initial insight and guide through. And of course, the quantum Hall that you see in the integers and fraction graphene, basically the important ingredient is how we understand those valley and the spins kind of arranges into this quantum numbers and so on. On the top of that, some of the stories are already Emmanuel mentioned that such as the kind of double layer system and heterostructures. A lot of the idea that now kind of plays a very important role in the two-dimensional electronics, the 2D material research. In fact, that a lot of insight that Allan initially provided actually kind of lasted quite a bit. So I'm going to tell you today that one of these, again, the analogies that I can just kind of make, graphene as a two-dimensional system, what type of these interesting the physics we can play kind of push forward again that inspired quite of the studies in Allan's previous work. So this story is about the searching anyons in the graphene quantum system, and I'm going to kind of share that the stories, some of them published and some of them unpublished. So the main people who did the experiments is the Tom and James, and now the Krishna joined there and the team. And the original work was done by my former postdoc Yuval Ronen, who is now in the Weizmann University, plays quite important role. We have the experimental collaboration with Amir Yacoubis and the theory collaboration with the Bert and the Dima Dwartmeier Brown. Okay, so the anion itself is kind of interesting object. We know in the three-dimensional, higher dimensional system, when you have any indistinguishable quantum particle, by just exchanging these particles together, that we have the only kind of two choices, either fermion boson, depends on the after exchange, how wave function changes sign or not, right? But once you get into 2D, there's other possibilities. Simply because in the 2D, the exchanges related with this the changing the positions and then winding this particle to another one has a good kind of the topological invariant, that winding number, and this will allows us that then indeed after exchanges particle, you get the phases other than just kind of pi or the 2 pi, and other possibility kind of comes around, and this was a kind of dedicated name of the anion in the system. Even further, that if the ground state manifold is degenerated, there's even possibility after exchanges you can map the one of the ground state wave functions to another one, and hence that even just non-abelian anion is kind of possible in this type of the system. And in the modern languages, in fact, this non-abelian anions, and especially non-abelian anion, becomes quite important because this is one way you can encode this quantum information non-locally and protect kind of by this topologies kind of built in there. And there has been some of this the theoretical proposals, indeed using this type of non-abelian anion, then one can just kind of provide this topologically protected quantum information processing. Experimentally showing this the existence of the anions, including abelian and non-abelian anion, has been kind of quite challenging. But we know that at least the quantum system, especially fractional quantum system, many of these fractional quantum system that their quasi-particle can to support this the non-abelian statistics, especially throughout the Jane sequences. We expect to see that the abelian anion comes around with the fractionalized charges, with this the fractionalized the braiding phase associated with that, as well as that some of this even denominator quantum state, that there are possibilities that one can realize non-abelian anions. So quite early on, the theoretical proposals is kind of clear that maybe quantum system is something that one can just look for the presence of the anions in there. Experimental proof actually requires the both of the proving that charges are fractionalized, as well as that there's a way that you can detect this braiding phase of these particles. And already about 20 years ago, there has been efforts that indeed detect kind of both of this quantity fractionalized charges, as well as the braiding statistic, braiding angles. And the one way that one can realize this type of the experiment is using the interferometry, especially so-called the quantum interferometer where you can send this electron or the quasi-particle through these quantum edges, guided by the edge of the sample. You can fabricate it or just kind of putting the gate. Here's an example of the Mach-Zehnder interferometer that they fabricated by, they studied by the multi-Hyperlooms group. And there are another example like the Fabry-Perot, the type of the interferometer in this particular case is Charlie Marcus's group's result. Over the past 20 years, there are quite a bit of efforts, experimental efforts, to realize those the quantum interferometries based on the quantum system has been realized in the gallium arsenide based on the heterostructures. Now, while you can see that main evidence here is by interfering the electrons through this kind of different path set by the quantum edges, the main observation you want to see that is that where the conductance of this interferometry, which actually measure the probability of this interfering electrons in the downstream, whether they can be modulated by both the magnetic field and the gate voltage. In this case, gate voltage changes the interferometer area such that you can modulate overall the Allan-Bohm oscillation. And that's kind of one way that you can detect kind of the phase information out of it. And that's kind of main use of this technique, right? When it goes with the fractional quantum states, where in principle you can pick up the abelian interference, there's kind of following the two experimental observables we can imagine. One is basically changing the gate voltage on the fixed magnetic field. You can modulate the total flux captured in this particular case, the Fabry-Perot interferometer, which actually modulate this the phase of the wave functions. And that phase, of course, is related with that phase, as well as the possibility of this braiding phase when you have this localized states inside. So in some sense, there are kind of two types of the information. First of all, there is some of this the regular information of the Allan-Bohm effect, which can be modulated by both of the gate voltage and magnetic field. And potentially there is rather randomly, unless you have to engineer this localized state, kind of that comes in the phase that coming from this braiding phase of this localized anions. And both of them contains one, the fractional charge information. The other one is the exchange phases out of this type of the data, right? While this is kind of straightforward, the prediction, experimentalists took it's about 20 years get kind of first glimpse that indeed one start to see that this both of the fractional charge as well as the exchange phase information. In 2020, Manfra's group at the Purdue actually beautifully showed that indeed they are well engineered this Fabry-Perot interferometer. Finally, they start to get this the Allan-Bohm phases where is a fractional charge information comes around. At the same time, there is this break of this phase jump, which actually related with this the population of the non-abelian anions. And by just kind of studying about this phase shift in terms of the careful connection with computation of this capacitance coupling, they deduced that this phase information is related with this anion occupation changes into the Fabry-Perot interferometer. About the same time, the Gendar-Febvre's group at in the Paris actually shows that slightly different the experiments. In this case, they use it quantum point contact and sending these pocketed anions through that and make the anion collide. And like the Holm-Mandel type of the experiments, just to look at the how the scattering happened between these two anions, they can also deduce that this the braiding phase out of this scattering experiment. And both of them, in some sense, is a very first experiment. The experimental evidences that shows quantitatively that indeed anion braiding phase can be detected in this type of system, showing this kind of really kind of important mark of this field. Now, of course, what I'm going to tell you today is now how we can just translate this experiment into the, again, graphene type of the two-dimensional system. There's kind of some of this, the incentive just to trying to do this experiment. First, of course, well, that the graphene provide the extremely high quality of the two-dimensional system, very approachable to the best quality of the gallium arsenide. So there is no reason we cannot do this type of the experiment. Furthermore, in fact, in the graphene, especially if you use a bilayer graphene, the bilayer graphene support a lot of the fractions, especially the even denominator the fractional quantum states, where that one expect to see that the non-abelian anyons much more robust than gallium arsenide platform, such that there is a hope that by just using the bilayer graphene especially, there is the possibility we can bring into the experimental technique rather quickly into the non-abelian anion case. I think that's kind of two important motivations out of it. Of course, in graphene, we don't have the gap into the system. So to try to kind of build up the interferometer, you need a little bit of the trick. The trick you need is, of course, first you need kind of extremely high quality graphene, which can be obtained by graphene encapsulated between the boron nitride, again encapsulated with graphite, such that all this kind of the heterostructures are all made of the van der Waals system. One can drive all these kind of impurities out as much as possible. But then you just kind of pattern this the gates around, and using this pattern gate, you can just put the different part of your electron in the graphene into the different potential and different carrier density. And under the magnetic field, you can just control the different the filling of the different part of the device rather easily, and which is a little bit more easier, much easier than gallium arsenide. In particular case, if you just put this the chemical potential into the near the charging neutrality point under the magnetic field, those kind of region becomes quickly gapped quantum Hall insulator, which actually we can serve as a depletion region of the electron hole, right? So in the end of the day, by patterning this top gate, one can just guide all the quantum Hall edge states throughout the device, and including this the quantum Hall point contact. And this plunger gate, often that we use, it's difficult to see in this here, that there is a plunger gate, which can control the area of this the interferometry, and measuring this downstream the conductance. You can see that indeed conductance oscillated as a function of plunger gate voltage or the magnetic field, showing that indeed we are seeing the Allan-Bohm oscillation of the electron going through. So integer, I think this one kind of beautifully worked it out. Over the time also, that within a year or two, because there are a lot of the information is accumulated in the gallium arsenide community over the 20 years, we can quickly improve our device even further. For example, instead of we have the global gate to control all this QPC, quantum point contact, which is the most important ingredient of this device. We can put down that the air bridges, which also we learned from the gallium arsenide communities, that separately control the quantum point contact very independently, such that we can fix all other parameters fixed, and simply just tuning this gate, we can just kind of teasing around this QPC, the transmission coefficient, which allows us that the kind of extremely careful control of the device the configuration. Out of this one, we can quickly show that indeed we can just demonstrate those kind of Allan-Bohm type of oscillation out of the integer, for example, not only just kind of one edges, but you can just kind of two edge configurations. For example, that you can just kind of see the interference outer edges, inner edges is kind of isolate here. Here that we are seeing the interference inner edges. With all these things is basically same condition, except the QPC the transmission is controlled, and you can switch one to the other one. You can quickly see that there is a kind of deep connection between this outer edge interference, inner edge interference. In other words, those phase slip point that we are seeing is nothing but just kind of the Allan-Bohm oscillation point of the inner edges. In other words, basically in this configuration, I can see that how the charge is kind of jumping into the inner edges appears as this kind of phase jump type of this experiment. Again, all of these things shows that indeed we have the really extremely good control of this interferometer, at least in the integer level. So once we get into this data, that we got pretty much excited that now we can just kind of drive the system into the fractional quantum Hall states, and at least we should expect very similar things what has been seen in gallium arsenide case appears. So here's again device structures I showed you. That experiment is very similar, except that now I just can put everything into one of the fraction, and just kind of try to look at the interference onto the fractions, right? Device quality is high enough that within, say, 12 Tesla, we are seeing the bunch of these fractions. This particular device is monolayer graphene. Therefore, we don't see the even denominator quantum Hall states, and one can just kind of apply this in bilayer graphene. Then surely at some point, the even denominator state will appear as well, right? So we had a great hope that initially, when we have this device, we should get this kind of beautiful data out of this device for the fractions. But the first shot of the data we got was rather disappointing, right? So 12 Tesla and 20 millikelvin, the same device I showed you, the beautiful integer quantum interference. If you go to the fractions, this is kind of data as a function of time. Nothing is being changes. Basically, all the gate and magnetic field is just kind of fixed. But you see that there is a kind of random noise appears here. So I think this morning, Hideo actually shows those kind of random telegraph noise coming from the unstable magnetic junction. Basically, this telegraph noise means that, well, there's some instabilities in my device. Basically, with this, I cannot do any more of the experiments, right? So I thought, at least when Tom, my students who took this data, showed me that, oh, yes, something's wrong with your device. Maybe we just can throw it out and just kind of make the device again. But Tom was kind of a careful person, and he just kind of staring at this one. It is a random telegraph noise, but there's some oddity here, right? Instead of usually 2 levels, there's seems like the 3 levels here, right? So there's a kind of 3 levels. You can see maybe the bottom is bigger and this one. So when we have the 3 levels and we are dealing with the 1/3 of the fractions or 4/3 of the fractions, then there's a remote chance that indeed, if there is the anion in this system, and if this is related to the anion number jumping, because of this, the anion number, the braiding phase is 2 pi over 3, 120 degrees. Within this sinusoidal modulation of the interference, there's always mode 3 of the relation, right? So if you have the 1 anion, 2 anion, 3 anion, and then 4 anion will just bring back to the 1 anion. Maybe those kind of 3 levels is related with anion number jump. Well, that is a remote possibility, and no one can claim out of this data that indeed we are seeing that anion braiding phase. But note that this experiment was done with everything fixed. So what if we start to change at least one thing? So what Tom did is just to take this data and start to change the plunger gate and ask what happens. And this is the data. Basically, those are 3 points we just measure is basically 1.56 the gate voltages. When he changes the gate voltages around, basically those kind of 3 levels that we can make the histogram start to evolve its own sinusoidal wave. And those kind of sinusoidal traces exactly 120 degrees apart from each other. In a sense, we are basically detecting that the anion number changes throughout this kind of the random telegraph noise, and that's basically what you are seeing here, right? So seeing this one basically really encourages us that indeed this random telegraph noise is kind of annoying, but it can be very useful tool that we can quickly detect kind of statistical evolutions of this braiding phases. In fact, that's kind of what theory already expected quite kind of sometimes. There are kind of theories that indeed, if there is a time variation of the anion number kind of occupation changes, indeed, you will see that this incomplete oscillation, which is 120 degrees apart, and those kind of things can be in principle detected by the experimentally, and that's kind of what we are seeing. And indeed, that's kind of related with this anion braiding number that changes. Can we actually detect the fractionalized charges? The way that we can detect the fractionalized charge is basically looking at this slope of the Allan-Bohm oscillation as a function of magnetic field and gate voltage, and the slope is related with the Allan-Bohm phase, which actually contains the information of the charges, right? However, the straightforward experiment for us is rather difficult, right? Because our phase is not stable, it's kind of randomly fluctuating. So if I just kind of don't change the magnetic field and sweep the gate voltages, basically it's already kind of rather random here. So the way that we can get this nice so-called Pajama plot to get the slope is almost impossible. However, look at this kind of looks random, but if I just kind of look at each of the places, each of them is more like the sinusoidal, but it was kind of here and there, just kind of phase jumps appears, right? What we can do instead of just kind of taking this Pajama plot is we just simply take the histogram, as I showed you here, all entire data histogram, we get this kind of 3 branches. And simply now, what if we change the magnetic field? And you see that change the magnetic field, those kind of phase that we got from this histogram is nicely kind of propagating. And surely enough, that slope that we are measuring here, which is equivalent here, is 3 times larger, the slope that indicating indeed we have the one third of the fractionalized charge into the system, proving that indeed not only braiding phase, we can see that fractionalized charge is effective table here. So the bottom line here is, although this is kind of annoying random telegraph noise, at least we can get the information about the braiding charges. So where this the telegraph noise comes around. Once we just measure temperature dependence, we start to see that as you increase the temperatures, that there is first of all, the visibility of the oscillation decreases because the phasing increases, but also you start to see that this the transition rate also got increases. In fact, if you just look at the transition rate can be so nicely described by this variable range hopping type of the stories. So we know that this is a rather random sites of the inside of the quantum dots. Anion quantum dots plays a role to create this type of the telegraph noise, right? Where they are and what is the nature of this one? Actually, around the same time that when we just wrote this paper and posted, it was not only us, and that my former group members like Andre Young's group and Yuval Ronen's group, who actually now has a group in the Weizmann, they also produce very similar data, but in some sense nicer data without random telegraph noise, right? So both of the group actually shows sometimes similar, sometimes slightly different devices, but clearly show that there's out-of-bomb patterns corresponding to fractional charges. There are some jump here and there, but it's not necessarily the telegraph noise is fixed in the time. So therefore, this type of the experiments, going back to that, you have to do the the capacitance analysis to detect this the phase information. Unlike this for us, that generally we get the statistics, right? So while that random telegraph noise is annoying, they did the good things. Then the second question is why we had more of the random telegraph noise than they had, right? It turns out that our cryostat we borrowed from the Amir's group has some interesting issues there. The issue here is that we just use a wet cryostat, which actually has this shield of this device is anchored 100 millikelvin rather than 20 millikelvin. So with the really remote possibility again, what if that indeed that some of these far IR photons or the gigahertz photon is in particular here is really kind of coming from 100 millikelvin hit my sample to create those kind of jumps, right? One way they test it out is what if then now we just kind of design that better, the sample shield, and just kind of really tightly covered my sample in the 20 millikelvin. Then start kind of suppresses the random telegraph noises completely. So we know that this type of the random jump comes from indeed kind of some kind of finite temperatures that tens of gigahertz of photon is the shedding onto the sample to create this random telegraph noise. Now we just try to use this as a kind of the tool that we can control this telegraph noise as well. All right, so I think that's kind of the some small cute story. Then we just kind of they put this nice work and post in the paper, and I thought kind of that at least that provide yet another way of the measuring this phase. After that, we post the paper. I got an email from the Shankar. Is it Shankar? Yeah. Okay. Yeah. So yes. Yeah. So I know that when I just post the paper a few days later, that I got the email from the Shankar. Without even reading the email, I know that I made some mistake there, and then, including not citing the Shankar's paper correctly. Yeah, indeed, that was the case. Shankar kindly pointed out that the mistake that we made, and including the citing his paper, that was actually very important, intriguing the point. I think that what Shankar and that the Reed actually pointed out is all this interference experiment, including my experiments that posted in there, and including even this gallium arsenide Manfras experiments. Basically, we cannot claim that this parameter tells you that the remeasuring braiding statistics angle. And the idea there is, of course, exchange versus braiding. Exchange is changing position, braiding is kind of coming around. So that's a kind of difference. I just argue in that way, but then Shankar has come back in a, no, you shouldn't call this a braiding. And it's actually this paper. The braiding was defined by mathematicians as just a kind of same operation exchanges. So one cannot call this as braiding. At the best, we can just say that this is double braiding or double exchanges, right? Okay, so that's a nomenclature. But there's a more important physics problem there. Because of this double braiding or double exchanges, there's a kind of the ambiguity in terms of the measuring phase. Basically, always experimentally, we can measure 2 times of the exchange phases. That's kind of what we just measuring in the experiments, which actually give you this sign ambiguity. Plus minus 1 is basically the same thing. In other words, basically, you just do this type of experiments, then you cannot distinguish electron, the fermion versus bosons. And then basically this kind of ambiguity comes in. Well, so that is kind of correct, kind of precise statement. So we actually made the changes in our the revisions in our paper. But on the top of that, there's a kind of interesting that the way that experimentally in principle address these issues. And around the similar times that, in fact, Steve Kiverson, that is the collaborator, posted this interesting experimental proposals. And the experimental proposal is the following way. If you have this Fabry-Perot interferometer, if you put the quantum dots, or the quantum, more precisely, anti-dots of the anyons into this, place in one of this, the QPC, in fact, whether this the anti-dot is occupied or not by the anyons, you will have the different type of this interference process. One, if it is emptied, of course, then the anyons can jump across the QPC. We'll get this kind of same the experimental situation we had without the dot. But if the dot is occupied, there's a kind of interesting cooperative tunneling process, which means that the occupied anion is coming out, and then the anions from the QPC jump into the dot, and its occupied anion is coming through the other side. Basically, that's a situation exactly the 2 anions change positions, right? And that's where that you should get additional phase coming from the external exchange phase. So in principle, you just compare these two, you should be able to just get the information whether there is indeed we get this kind of braiding phases up to the sign. Of course, installing such a quantum dots into the QPC is almost crazy idea at this point of the technologies we have to fabricate a device. However, nature is kind enough because there's enough number of the disorder, especially near the QPC and right at the QPC, whether there's a shallow disorders around. In principle, that by just kind of tuning around the QPC gate around, we should be able to find out that those kind of the resonances coming from this accidentally formed the quantum dot in the QPC area. Indeed, this is one example that when we just tune QPC the gates around, you can see that when this the QPC conductance is crunching off, there's some sharp kind of resonance type of peaks comes around. When we just kind of bias the source and drain bias voltage one of this dot, you start to see that so-called the quantum dot type of stability diagram start to shows up as a bias voltage and the gate voltage. You see the diamond shapes and kind of QPC type of the things comes around. 1 minute, yeah. Indeed, if this is the quantum dot, then we can see that by just kind of looking at the one side or the other side of this the resonance peak, one expect to see that the anion number got changes, right? Indeed, when we just kind of look through this the interference pattern, left and right side of this QPC, we see that the phase shift of the 60 degrees or equivalent to 180 degrees appeared this 2 different interference pattern, clearly showing that we got even just kind of half of 120 degree or 60 degree of the phase shift out of this data, indicating indeed we can just pick up this type of signals as well. I think this is kind of indeed now one step forward, which has not been done in the gallium arsenide. All right, so I think that's kind of story I wish to share with you with this really high quality of the graphene 2-dimensional systems available. Now we can see that the fractionalized charges and their braiding phases. I think this kind of very exciting platform. As I said in the graphene, that we have the much more flexibility over the gallium arsenide. So now we can just kind of install the anti-dot, which we can control by the gate voltages that not rather than randomly jumping around, we can control this anion population, hopefully, and extending into the bilayer graphene, we can just expand this experiment to the even denominator state rather quickly. So that's kind of all I want to say. Again, I want to kind of thank my collaborator, but more importantly, past the 20 years of the guide and the mentorship that Allan provided me up to the here, and kind of big thanks for the Allan again. Thank you.
Thank you, Philip. Since we're about 4 minutes over time, even though the organizers told me, don't worry about the clock, we have plenty of free time. I think maybe one question while the next speaker, Feng Cheng, is getting set up. Anyone?
I'm just curious, when you change the
Yeah.
you change the density in your do you worry about ever changing the density out of the 1/3 state, or
So that's kind of, you have to design your gate structures kind of quite well. So when you change the plunger gate, simply that you change the area, right? Kind of rather than density gradient in there, right? So that's kind of important. So I think that the kind of important technologies developed, that's kind of the success of the, again, the Manfros group types of the data. There, you have to put the kind of one of so-called the screening gates nearby, such the electrostatic is a kind of right part. Just kind of the density gradient is not getting the inside of your dot as much as possible, right?
Hi, thank you for the talk. I'm wondering about this random noise you have.
Yeah.
You showed. It's very nice that you can identify the non-abelian statistics even from the 3 levels. But I'm wondering if that could be a limitation to fault using this phase for fault tolerant
Sure, yeah, of
quantum
course.
computing.
Yeah, that's useful for just to get the quick statistical averages. But of course, in the real device, that's kind of not nice. So we know that where it comes from is probably the black body radiation from 100 millikelvins of the environments we had. So we cut it down, then we get rid of the most of this random telegraph noise.
Okay,
so don't worry about that. We need a low temperature though.
But in principle, so the ground state itself is topologically protected, which means that small perturbations won't affect your state. But this mixing between the 3 degenerate ground states,
yeah,
that can be, as I think, as you showed, they can be mixed together even by small perturbations. So it's kind of a mixing that goes beyond the topology,
yes.
right?
By the way, so the data that I showed is abelian anion, so it's not associated non-abelian anion yet, but I think that the statement is kind of similar to there. All these protections, either abelians or especially non-abelian anion, is based on still that gap with everything's within the gap, and the gap is basically whatever fractional quantum state gap, right? So I think the topological protections that we are talking about is still within that the size of the gap in non-abelian anionics, the fractional, even denominator fractional quantum state, for example, which in the graphene is something like the range of the few Kelvin. So I think still that everything's, all the fluctuations or the random events, the perturbation should be within the gap such that we can just have the protection. If you just go beyond that, we don't have the protection.
Okay, thank you.
Yeah. Thank you.
Thanks, Philip.